Hello and welcome back, everybody. This problem right here is one that probably looks familiar to you because there's a good chance that we did it in class already. Example 2.5. The one where the boat is moving through a marina and then when it passes the breakwater it throttles up. We may have already solved this one in class, but if we did, that's okay because this video is going to be a slightly different take on this problem. Instead of solving it or I should say, instead of kind of visualizing it algebraically, we're going to see if we can visualize it graphically by using just a graph. And so I'm going to shrink this down here a little bit because I want us to make 3 stacked graphs that kind of pictorialize what this boat is actually doing. Let's see. I'll put it over here in the middle. Okay, so we're going to create 3 stacked graphs, and if you've done the stacked graphs lab already, this should look familiar to you. The way we're going to stack them is like so. It's going to be 3 XY graphs, one on top of the other. Okay, and it's going to be position versus time on top. Let's see, I'll do that in blue. Position versus time. Velocity versus time is going to be in the middle. That's going to be green. And acceleration versus time is going to be on the bottom. That's going to be red right there. Okay, squeeze that in. And all we're going to do right here is simply, I'm going to move this back up to the top here, is simply graph what this boat is doing. As it moves through the marina at a constant speed and then when it passes the breakwater. So let's just go back and read it real quick. A boat moves slowly inside a marina, I guess, with a constant speed of 1.5 meters per second. Okay, constant speed. As soon as it passes the breakwater, it throttles up and accelerates at 2.40 meters per second right there. And then it asks how fast is the boat moving after a certain amount of time, and how far has the boat actually traveled. But instead of solving it the traditional way, like algebraically, let's see if we can sort of envision this graphically. What I want us to do is actually start in the middle graph, the velocity versus time graph. Actually, let me back up a second. We want to do one more thing. I'm going to draw a little dotted line right down the middle there, here, and here, because what we really have is we've got a change in the boat's motion. That is, it went from having a constant speed to having an acceleration. All right, so this line is going to be before and after it passes the breakwater. But all right, back to what I was originally saying. Let's go to velocity versus time. How would we describe its velocity before it hits the breakwater? Well, it's got a velocity of 1.5 meters per second. All right, and so let's draw that. I'm going to call this 1.5 right there, 1.5 meters per second. And it's constant, because over time, as it's moving through the marina, it's not changing. All right. What's also true is, let's plot these graphs before the breakwater, and then we'll plot them all together after the breakwater as well. All right. So if it's got a constant velocity, that means that the acceleration is what? A constant velocity. The acceleration is 0, right? So for that period of time, however long that is, we're going to have a flat line at the 0 y value on the acceleration versus time graph. Okay? Then, let's ask ourselves, all right, what does the position versus time graph look like right here? Well, remember, it's got a velocity, so it's got a constant velocity, so it's got a constant change in position over time. All right? So change in position over time is that over that right there. So that means it's going to have a constant upward slope. And that's what we said in our stacked graphs lab, if you've gotten to that yet. That is, the slope of the above graph equals the y value of the below graph. So this is 1.5 meters per second constant, and that means the slope here is 1.5 meters for every second. Okay? But what happens then when he finally passes the breakwater and the boat decides to speed up? All right? Well, it accelerates. It goes from having no acceleration to some acceleration, and it's going to be at a positive acceleration because it's moving in the positive direction. So that positive acceleration, what is it? Well, it tells us 2.40 meters per second squared. So is the acceleration changing? Well, actually, it is changing from before the breakwater to after the breakwater, right? But once it passes the breakwater, it is a constant acceleration of 2.40 meters per second squared. So we're just going to go to 2.40, wherever that is, maybe right there. And we're going to draw a line straight across, because that indicates now our new acceleration. By the way, I a lot of times connect them. Some people say it's not mathematically correct to connect graphs like that, but that's just so that we can see them a little bit easier. Okay. All right. Well, what does this mean then for the velocity versus time? Well, remember the y value of the below graph, which by the way that was 2.4, right? It was 2.4 meters per second squared. 2.4 meters per second squared. The y value of the below graph is the slope of the above graph right there. So that means this y value of 2.4 meters per second squared is going to be a slope of 2.4. So it's going to be a positive slope to the tune of 2.4. 2.4 what? Meters per second, right? Velocity over time, or meters per second squared. So the units are the same. So this indicates the acceleration too, but the slope indicates the acceleration. Here, it's the y value itself indicates the acceleration. All right, well, what does that mean then for our position versus time graph? If you've got a change in your velocity, so your velocity is different, the y value of your velocity is different here, 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 and as we go up, we've got a greater y value right there. That means that the slope of the above graph is going to be different. It's going to be increasing. So I hope I left enough room for this right here. It's going to be going kind of like that, and I'm going to go off the page. All right. The y value is getting greater as we go up. So therefore, the slope is getting greater. Greater slope, lesser slope, even lesser slope. Okay? The y value on the lower graph equals the slope of the upper graph right here. Okay. Last thing we're going to do is we're going to see if we can graphically solve for how far the boat has traveled in this amount of time. All right, now the amount of time after the breakwater, so really all we care about in the problem is what takes place after this point, after the breakwater right there. The amount of time that elapses is going to be 5 seconds, okay, or 5.00 seconds. And what we want to know is the displacement, or how far it has traveled in that amount of time. And now I'm not actually going to solve it, but I'm going to show you how you could solve for it graphically rather than algebraically. All right. Remember, we say that the slope of a position versus time graph, of a velocity versus time graph, is the acceleration value. Okay, but the shaded area underneath the graph for a certain amount of time, in this case over 5 seconds, is going to be equal to our displacement for that whole amount of time. Okay? So, let me make the dotted line right here, because we really have two areas that we need to find. This bottom area right here is just a rectangle. And so I'll call that displacement 1. That's going to be 1.5 meters per second. Let me erase that a little bit. 1.5 meters per second times what? Well, 1.5 is your vertical. Your horizontal is the amount of time that elapses times 5 seconds. I left the 5.00 off right there. All right. So this area, this shaded in area, in fact, I'm going to draw it like with a different pen. Oh, I can't. All right, never mind. I'm just going to just shade this in kind of like that. Now, the whole bottom area right there is the base times the height. All right, so that's a certain displacement. Displacement 1, we'll call it. Displacement 2, delta x2, I should say, is going to be what? Well, it's the area of this triangle. And you guys know that the area of a triangle is 1/2 base times height, right? So that would be 1/2 base, which is 5 seconds, times the height. All right, what is the height from here to here? Well, it's the change in velocity. It was originally at 1.5 meters per second. We don't actually know the final velocity, although if you were to do it this way, you would have solved for it in the first part of the problem. How fast is the boat moving after accelerating for 5 seconds? So you would know that by now, but that's okay because I'm not going to solve it right now anyway. So you take 1/2 base times the height. 1/2 base, which is 5 seconds, times the height, which would be your change in velocity. Okay, and that would give you displacement 2. This here would give you displacement 1. Oh, I dotted my 1 again. I do that a lot. It looks like an I, and it should actually be a 1. What I'm saying right here is this, that if you can find this area and this area right here, given what you know, add them together, and it should be the amount of displacement for the whole boat for that period of time. All right? That's the idea. The upper graph slope is the y value of the lower graph, but for a certain amount of time, the lower graph's shaded area tells us about the change in the y value of the upper graph. By the way, for our acceleration versus time graph right here, what would this shaded area be right here? That would be our change in the y value of the upper graph, right? That would be our change in velocity. It would tell us how our velocity changes from here to here. And actually, we could do that. We could find out what that change in velocity is and stick it right in there because we know it's 5 seconds, and we know that the acceleration is 2.4 meters per second squared. So we could find that change in velocity, stick it in there, and then find our delta x2, add it to our delta x1, and we'd have our total delta x for the whole area. Oops, I'm drawing it in red. Oh well. And I just erased everything because I hit the back button. Darn it. Which would equal our final displacement. All right? Sorry about that, you guys. I just kind of erased everything, but if you rewind, you'll see what I had written right there. That was going to be about it. I want you to kind of understand how the slope, the y value, and the area under a certain amount of time graph are related, and we're going to do that more as we move forward. All right? In the meantime, thanks for watching, and look for me on the next example problems. Thanks. I'll see you later.